Ladies and gentlemen, I wish I could say good morning to you. The morning is not good. My relatives in Kiev have been awakened by rocket explosions. Not only Ukraine, but we are all under attack by a criminal gang. What shall we do? First, accept it and perhaps get rid of some illusions. Second, we shall recognize that panic, grief, hatred. This is precisely how these criminals want us to feel. And with that, we shall believe that justice will prevail and the criminals will end up behind bars that they belong to, and we can concentrate on our immediate tasks. Good. Let's go back to advanced quantum mechanics. Today is a crucial lecture of the course. Today we will finally learn what's the proper way to proceed. Not that it will learn much about physics, phenomena, but we will understand how to proceed. What would be tool set to apply, to learn, to describe, to think, and eventually to pass the examination. Right? So it's a topic of second quantization. What are subtopics? We will start with creation and annihilation operators, just by introducing it. And we'll try to remember what I told you about the motion, what I told you about the dance. We do something, we manipulate objects. We start very simply, we look at the products and understand the relation to occupation numbers, and commutation rules. Then we turn to field operators, and we will able to rewrite the Hamiltonian in terms of field operators or creation or annihilation operators. Otherwise, they would remain a mathematical object. Otherwise, they would not help us. Good. With that, we can actually concentrate and understand why it is called second quantization, what are the consequences. That I will all do for bosons. After that, I will switch to fermions. Most of the time, I will just repeat what I said for bosons, but there are important differences, of course. Fermions are not bosons. Good, so hopefully, although I have almost infinite set of transparencies, we will get through, and we will end up with a short summary of second quantization rules and applications. Good. Where shall I start? So we are working with bosons. No, let's see. Sorry, sometimes it's difficult to concentrate. Please excuse me. Suppose it's bosons, although at this transparency it doesn't matter. We will start with a point we have started the previous lecture. We start with a set of states for a single particle. We will label these states. Sometimes I will call them levels with a letter K. As an example, K could be discretized wave vector of a particle in an empty space. But it doesn't have to be. Any set of single particle states will work for us. Good. Then we take what we have learned in the previous lecture. What we have learned, it's Fock space. It's a Fock space, and it has many base vectors. All of them are uniquely identified by a set of occupation numbers. So there are levels, and in each level you have integer number of particles. That long row gives you an idea of a vector in Fock space. All right, all these vectors are orthonormal. That's what I put here. So that object in curly brackets, let me remind, it stands for a long row of numbers. Very good. Now, crucial step, and that doesn't seem to be very harmonic. I would say it's even ugly. But anyway, what we will try to do is introduce an annihilation operator, A. That operator will have an index K, which means that we annihilate a particle in a certain level K. Right. So what does it do to the state? Right. It acts on a state with a certain set of occupation numbers, and it will change only occupation number with K. Right. It will decrease it by 1. In addition, and if I would to introduce annihilation operator, certainly I would introduce it without this ugly factor, which is difficult to remember. But I would have been wrong. The factor is in its place. We will see it in about a minute. Good. Next, we initial conjugate this operator. What does it mean? It means that you switch the indices and you complex conjugate the elements of the operator. Well, in this case, elements are real. Complex conjugation I just had done. But the order of matrix elements has changed. So, in this case, A dega just increases the number of particles in the level K, and conjugation gives the same ugly square root. That's it. Circulation and annihilation operator. There's always a difficulty to memorize this because, our culture is Christian-based, and in our culture, cross is associated frequently with death. While a cross, a dagger, does the opposite. It increases number of particles of one and creates a new particle. Okay, two ways to memorize. If you're kind of agnostic or the atheist, then you could safely say it's just plus. Plus, it adds a part. Or if you're a true believer, you could say that death is eventually a way to new life. Very good. What we can do this? Well, natural instinct would be to do something with this operator. What we can do with operators? Yes? Not time yet for time evolution, something simpler. You cannot throw it away, they're not blocks. You cannot put it floating, they're not ships. What we can do? Count the number of particles. Review, but in which way? I want a simple word for you. Yeah. That we could, although I believe we would end up with zero. It will come. Let's start with something really elementary. What we can do with operators or matrices or any object like this, we can multiply them. So let us start with this. We'll see if anything interesting will happen. Good. So we will multiply them. I do this explicitly. It's one of few places in the course I do it explicitly. Many things I would presume you do. I don't like to talk about unpleasant things. You do when you self-study the material of the lecture and look at these slides again. Please be advised that the slides are not really only to look upon. There are some simple calculations which you would do while processing the slides, either in your head or on a piece of paper or whatever. Right, let's multiply. So first we let this operator to act on the state. All right, what we have is expected by definition of the operator. We have this square root, and number of particles in K is dropped by 1. Now we let the creation operator to work on the state. The number of particles is back to normal. And these square roots multiply and give just number of particles, occupation number of this mere level. Good. That is the use of the square root. We can establish a link between the separators and occupation numbers. Fine. We can do something useful. For instance, we can write the operator of total number of particles. We just sum up over all levels, and we got the total number of particles only in terms of creation annihilation operator. First, little use of these objects. All right, good. We have not exhausted yet joys of multiplication. So let's multiply it again. Sorry. But now in a different order. Let's see. First we create. That gives this square root. Then we annihilate. The state is back to normal. The state remains the same. And there's a factor which is different. The factor is nk plus 1. Fine. What we can conclude? We conclude that the commutator of these two operators is unity matrix, whatever the states. Yeah, we can check it for every state, and for every state, this nk would cancel in commutator. General property, interesting, that doesn't depend on states at all. It just reflects the properties of the operator. Some people eventually don't like how I draw on slides. I would say it's for your own better, it's also for my own better. When I annotate the slides in such a way, first I tell us where we are in the slide. Second, I just stress something or perhaps comment on something. I would really discourage you to copy my annotations during the lecture. It's not intended for copies. Not because it's classified, no, not at all. It's just because the slide by itself suffices for all information content. Good. So we establish commutation rules. Let me put it in more general framework. I could kind of prove the same with calculations, but at this moment it's again for self-study. If k and k prime is the indices of these operators, different operators conveniently commute. Right? So that's the general commutation relations. And also, if it's not A dagger A, but AA or A dagger, they commute as well. Right? Kind of a proper way, a little bit more abstract way, which we don't use now, would be just to start with these commutation relations, which I haven't postulated, I haven't derived them. I could postulate those and then derive, for instance, the existence of Fock space, get all states in Fock space with the 8 of these operators. So it could be an equivalent starting point. Fine. So let us talk more about this. Let us understand the structure of Fock space and how creation and annihilation operators are helpful in this construction. First of all, let's talk about vacuum, which is usually defined. What is vacuum? Who can tell me? Yes, or one could put more visual a definition like empty space, nothing at all. Strict definition of vacuum is a little bit different, although it is consistent, of course, with the previous definition. By definition, all annihilation operators, when acting on the state, will give you zero. And what is zero? Zero in quantum mechanics means end of program, mistake, like division by zero. Right? Why is it so? Because you cannot normalize the result of zeros, or action of the operator doesn't give you a wave function, it just gives you zero. Okay. That's the definition of vacuum. What does it mean? It means that if you try to annihilate anything in vacuum, it just doesn't work. We don't have eligible quantum state. Very good. Okay, it's a bit boring. Let's try to apply creation operator. And right, we shall understand that since creation operators conveniently commute, we can make any basis vector of Fock space, any set of occupation numbers, just by applying sufficient number of occupation of creation operators in each block. That's the formula, right? So it's a product over all levels, and in each level, I have created nk particles. I have applied the operator nk times. Good. Then we got a wave function which has to be normalized. And right, it's a normalization coefficient. Which looks ugly indeed, but well, as we will see, it will hardly come in any practical calculation. But it just to keep in mind that all basis vectors of Fock space can be created in such a way. Another concept which I would like to invoke is a concept of navigation in very complex and multidimensional Fock space. To introduce the concept, let me consider an ultimately simple case which allows for visual representation. Namely, I would say that I have only two levels, 1 and 2. What would be an arbitrary state in Fock space? All right, that will be characterized by two numbers, and I could put these states as points on this integer grid. Okay, then let me draw creation annihilation operators in this basis. There are two creation operators, A-1 and A-2. What do? They just move the state from one point to another. That we have created two particles in level 2. We could create two particles in level 1. Or we could go to 1, 1 like this, or like this. There is no change because of commutation of the operators. So that we could do for two levels, which is 2 dimensions. It's a kind of very convenient visual. How one could do it in multiple dimensions, that seems impossible. Dimensions are too many. There's infinite number of levels, and in each level we have also infinite number of possible occupation numbers. It looks like it's beyond human abilities, but well, I don't know. I don't know about your generation. Yet 3-4 generations ago, the students earned some little money with web design. You know web, internet, right? Design. Who masters PHP in audience? Who have heard of PHP? Oh, great, good. So one could write a simple PHP script which would allow you to navigate in fog space. All right, I wouldn't dare to put it as a working task, but if you like programming, you could give thought to this concept. It's very useful. Fine. Sir, we have mastered creation and annihilation operators. I want to put your attention to the fact that we haven't been quite democratic. Why is it, sir, and what is actually democracy in quantum mechanics? Generally, in quantum mechanics, it means that all equations, all predictions, calculations can be done in an arbitrary basis, right? Like all geometry, three-dimensional geometry can be done in any coordinate system. Fine. So let us try to set creation annihilation operators in a different basis, in a different representation. So at the moment we are working in representation of energy levels. Let us try to construct something in coordinate representation. First, let me remind you to go to coordinate representations for wave functions. If we know the wave functions for our levels, here they are, and the coefficients or superposition in the system coordinates of our wave function, projections of our wave function in the system of levels, all right, we can restore coordinate representation like this. That we did with wave function. Now let us try to do the same with operators. To this end, I will replace the wave function in level representation with annihilation operator. What I get is an operator which depends on coordinate, psi of r. As an example of wave functions, I could concentrate on plane waves, but as I said, it doesn't matter much. The object which I ended up with, is called field operator. Field, because as we discussed in previous lecture, there are no particles. There are no particles, there are only quantum fields for identical particles. Right, what's its kind of meaning? Psi r annihilates a particle not in a given level, but at a given point. Psi dagger correspondingly creates a particle in a given point. All right, so they are operators. They do something. Fine. So we kind of enriched our tool set. Let us check commutation rules. For these operators. Okay. I don't want to do it explicitly. Because you also do not want, but again, to understand what's going on, I would advise you to decide. Let's understand what one has to do. One has to take expressions of psi in terms of A. Substitute into these commutation relations. And then make use of commutation relations for A. In this way, we end up with the following. The commutator of creation annihilation field operators would be delta function. It's an analogy to a commutator of A and A dagger, where it is at the same level. Here it is at the same point. All other commutators are 0. And right now I could talk about some physical values which one can make from these operators. Let me make density operator. Density operator shows what is the density of particles in a given point. Here it is. Again, it's analogous of expression for AKK, which gives number of particles in a given level. Now we get number of particles at a given point. Right? Density. Now we are heading towards Hamiltonian. Let us start first with non-interacting Hamiltonian, which, as you know, is a sum of single particle Hamiltonians. You might remember how inconvenient was that, because number of terms in this Hamiltonian, well, it depended on number of particles in hand. So it would be difficult to write it in general form. Here, it's a piece of cake. Let's see how creation annihilation operators help. First of all, let us recall the energy in terms of occupation numbers. There are level energies which, there are epsilons today. Interesting. Okay, there are epsilons today. Epsilon K is the energy of level K. Right, times occupation number. Now we can substitute AK, A dagger, K, AK instead of this occupation number. Here we are. That's a Hamiltonian free particles. It's a quadratic form in terms of creation and annihilation operators. Good. Then I want to show you some formula. And okay, you would, yeah, it's not that one should not do it at home. It's something which is useful to do at home. But well, expect a little bit of a difficulty. Let me tell what one does. It's again change of basis. We're going from representation in terms of energy levels to coordinate representation. To this end, we look at this formula and revert it. It's a reversion. I could do this reversion only, I could do it in simple terms, only if this FKR, phi KR are basis vectors of an orthogonal basis. So that I just multiply this equation with what? I have an equation, I want to multiply it to get to this one. Yep, indeed. Phi, not sorry, phi, dega, k, depending on R. Then integrate over R. And these basis vectors would be different k, right? Say, let us call it L. And that integral owing to orthonormality, it looks terrible, but it's just delta KL. So that's how we come to this relation. Oh, pardon. It's not yet all. We need to substitute. We need to substitute A's in this form. And then we will have the Hamiltonian in the basis of wave functions, and that we can rewrite in coordinate representation. Good. Single particle Hamiltonian in coordinate representation is pretty much known. Here it stands. So potential energy, kinetic energy. Now it gets sandwiched with two operators, this field operator on the left, field operator on the right, and integrated over all R. Yes?
So is AK there still an operator?
AK is an operator, yes. Good, so Hamiltonian in coordinate representation can be expressed in terms of field operators and the single particle Hamiltonian in our representation. Let's see how we're doing this time. So far, so good. Let me talk about something which is a little bit more complicated, but we have to get through. Let me understand how to describe interaction in the language of field operators or operation annihilation operators. All right, let us see. That's what we get in Schrödinger equation in terms of particle coordinates. Summation over all pairs of particles. We talk about this on Monday. Let me rewrite this formula indeed. First, at classical level, sir, here density is not an operator yet. Okay, I can implement this formula to rewrite the energy in these terms. Good. So what's the difference? Here I have no integration. Here I have two integrations. But I integrate eventually a set of delta functions, right? Two densities. Each density is a set of delta functions, right? So if I do this integral, I would just have sum over all pairs of the particles. Good, we come to this and now we quantize, we replace density by the operator. Fine. There's something else we have to take care of. Unfortunately, if I would just end up with this expression and just took a single particle, localized somewhere, well, it has some density, right? It has some density, and that density would produce some interaction. Self-interaction of a particle, it's a fascinating concept. Fortunately for us, it's completely unphysical. Very good. Let's forget about this. And then we understand that we have to subtract self-interaction from here, as I would subtract terms with same particles in this expression. So a particle doesn't form a pair with itself. All right, so I subtract. Now I understand what I have to do. I have to substitute density in terms of field operators. Let us see. Does it work? Fine. I do it. And let me attract your attention to the order of these operators. If I would just multiply two density operators, the order would be psi dagger, psi, psi dagger, psi. I rearrange it a bit. Why? just implement this. I want to subtract self-interaction. So I use that the commutator of soup size. You have seen that, huh? Don't forget. Is delta function. Let me check if I did it okay. So here I have two annihilation operators of two particles, which means that this operator would give 0 if it works on a 0 particle state or 1 particle state. One needs 2 particles for this operator to give something sensible. That's right. That is the interaction. For 0 particles, for 1 particle, we don't have any interaction at all. And now as you have noticed, I am playing this coordinate representation and level representation again and again. Some things are convenient to formulate in level representation. Some come naturally in field operator representation. So interaction I got in field operators. Let me come back and let us express it in terms of creation and annihilation operators. How would I do this? Nor black magics, not at all. I just use this formula and I take plane waves. That's natural to do for plane waves, right? If I do it in plane waves, I have operators with different wave vectors corresponding to momenta. And I note this wonderful thing, very useful, momentum conservation. So what does it mean? I create 2 particles with K. This. Okay. 2 particles with K and K prime. And they have been annihilated with the momenta K plus Q, K minus Q. The momentum of 2 particles stays the same. Momentum conservation. All right, how one can picture it. These pictures look like Feynman diagrams. They're not. Feynman diagrams is a bit something more advanced, but it's always convenient to draw pictures instead of long formulas. So there is a picture for a term out of the sum. I have 2 particles created with K and K prime, and they are transformed in 2 particles with corresponding wave vectors, and that looks like a scatter ring of 2 particles on each other induced by this potential. They kind of collide and change their momentum. Good. So we have derived expression for interaction, and you see that this expression already contains 4 creation annihilation operators, in contrast to 2 for non-interacting particles. And 4, it's a bit too much, so that makes actually advanced quantum mechanics complex signs, unsolvable, not solvable readily, also with computers. That makes the problem challenging. But not at this step. At this step, we just have a goal to get Hamiltonian in terms of these operators. Fine, I guess it's time for I would say 5. Okay, let's make it 8 minutes break. Very good. Let us proceed again. Let us see what we have done. And face consequences. Good. We still with bosons. Although, as we will see, for fermions, the changes are minimal. There are still 4 operators. Expression for interaction in terms of creation annihilation operators, so field operators. 2 here, I've forgotten to say this, stands for 2 particles in 2 particle interactions. Control question. Say I wanna treat 3 particle interaction. How many creation and annihilation operators would I have to involve?
6.
Yes, that's 6. So each particle kind of gives you 2 particles 4, 3 particles 6. Right. Let me do Heisenberg. We did learn Heisenberg picture. We did not do it in vain. We will apply it here in our course because many formulas involving these operators are really very handy in Heisenberg picture. Because it's about evolution of operators, and as I already hinted a bit in the second lecture, we don't want to know much about wave function of many body state. It's got to be very complex. Simpler to live with operators, fine. So what's the Heisenberg picture? Wave function doesn't change. Operators do, according to this formula. Time derivative of an operator is a I times commutator of the Hamiltonian with operator. We need a Hamiltonian that we have. All right. Now let us talk about field operators in Heisenberg picture. Let me start with creation and annihilation operators in the system of levels. Here, equations are simpler. I want to say the time derivative of annihilation operator. If I would go for creation operator, what do I have to do? Well, it's just complex Hermitian conjugation, not a big deal. So I need only derivative of annihilation operator. Fine. And it's given by this Hamiltonian, this commutator. And H is single particle Hamiltonian, sum over K, epsilon K, A dagger K, A. Right? So one has to do this little commutator. Again, I don't want to do it explicitly here. It's a task, but it's a task which is best is made at home. You remember about dance. Don't dance, then sorry. Right, so what's the result? The result is astonishingly simple. You got the same operator with a factor which is epsilon. One can solve this equation easily, but let's pause a bit. Let's rewrite it in terms of wave functions leading to derivative of a field operator. Right? We remember how to do this. Instead of A, one would substitute size and wave functions, work a bit with wave functions to come to this expression. Right. Psi. Who recognizes this equation? Yes? Yeah, it looks precisely like Schrödinger equation. That's a point and the point of big confusion. That's eventually why all this set of methods has been called second quantization, which is good as a slogan, but well, whatever. It's really stupid to argue about notations. Second quantization. At the moment, let us understand that equation for a field operator, which is no wave function, coincides with Schrödinger equation. Right, but the name eventually arrived from comparison of these two equations. Schrödinger equation for a single particle and Heisenberg equation for evolution of the field operator. Right? They formally coincide. That it looks like we have promoted wave function to an operator. Say, in usual quantum mechanics, we start with classical variables like x and p, coordinate and momentum, and we promote them to operators, give them hats. Here it looks like we gave a hat to wave function. We have quantized it to make it an operator. What one could say again, one could, for instance, average this operator over a wave function, a non-wave function, and for expectation value of this operator, one gets already scalar equation. Right? It's a comparison with the first quantization of classical variables promoting the into operator. And the second quantization also gives non-commuting size. But let me make myself clear. This is just notation. This is just Renaissance, mnemonics. Wave function is there. Wave function does not change its meaning in advanced quantum mechanics. And similar equation we have for an operator, which is not a function. Any questions to confuse you further? Yes?
I want to call the Schrodinger equation for the operator. Since we talked about operators applying to something,
That's precisely the part. That's precisely the part. It's an operator, we applied it to something. We applied it to wave function. Wave function is never gone, it's not got quantized, it's an operator. But just for the sake of confusing students, this equation looks pretty much like Schrodinger equation. And that gave the name to the stuff, because well, people in 20th of 20th century, they really thought that it would make sense. So, okay, I'm done with second quantization. That's what we need to know. Creation relation operators, field operators, Hamiltonian in terms of those. Right, we did it for bosons. Let me do the same for fermions. There are differences and similarities, more similarities than differences. Right, so is it cut and pass from my relative transparencies? No, there is a difference. There is a difference, but the difference is only in an example. For bosons, I could use an example with k vector. Fermions intrinsically have spin, at least fermions that we kind of are accustomed to, right? So this label of a level would also include spin, plus minus. But as far as we keep these notations, that doesn't matter much. Good, so this Fock space, and it's made from basis states, and each basis state is identified by a set of occupation numbers. As earlier, what is the difference with bosons? Now these occupation numbers can only take two values, 0 and 1. Right. What will be also useful for me as a kind of mnemonics is the following. Due to the fact any basis vector in Fock space I can present as a sequence of occupied states. So again, I have a long list, long row, but it would be the list of occupied states. Here, for instance, here, second state is occupied, third, fifth. So I write it like this. A set of numbers which are ordered at the moment. Fine. So what will be the next step? It's not a proof, it's rather mnemonics. It's something which I want to do. So it's not, yes, a soup. It's just a receipt to do the soup. Right. If I put these levels in another order, like instead of 3, 2, 3, 5, I would put 2, 5, 3. I understand that I exchange the particles. right? And if I change the particles, I need to recall that the fermions and the wave function changes sign upon commutation. That's why I'd like the creation operators anti-commute for the different levels to account for this sign difference. So for bosons, it would be no difference between 2, 3, 5 and 2, 5, 3. Here it is. And I would like to incorporate it in the order of creation operators. Whether I create electron n5 state first and then in 3, or first in 3 and then in 5. Good. So this is a want. Haven't achieved this yet, but it's a kind of motivation. And now I give the definition of annihilation operator for fermions. We have been already confused with annihilation operator for bosons. It's been an ugly square root. Here, the confusion, well, I would say even deeper. Although it might look a little bit marginal. All right, what this operator does, it annihilates the particle as we expected, and it might change or not change the sign of the state. And how does it decide upon that? Oh, that's really confusing. If I were Pauli, I would never ever dare to write such a definition. But there are very daring people. That sign eventually counts how many particles are there in this interval, right? It sums up it overall k, which are smaller than k it works at. And depending on this number, whether it's even or odd, the wave function is multiplied either with plus or minus 1. Look, guys, that looks crazy. Why? Who could give me a good argument to witness my madness? The answer for this, for this operator does depend on the way we have ordered the levels. But yeah, physically it has no chance to depend. There are some levels, you can call it 1, 2, 3, 5, or we can renumber it. It does not change physical situation. Not for this operator. Good, so our conclusion, our sentence, is this operator unphysical? Shall we conclude our course right away? No, we should not. Because physics is such a science that it uses quite many unphysical values. Just get used to it. Who can give me an example?
Vector potential?
Yes, for instance, vector potential, right? We can invoke vector potential to describe magnetic field, and it's conveniently it is convenient to have different choices for different problems. Different vector potentials to describe the same magnetic field, the same physical quantity. But I kind of want to have a simple example. Simple example is voltage. We've been talking about voltages many times, but let us recognize that voltage by itself is not a physical value. A simple practical example. If you just grab a wire at voltage, I don't know, 10,000 volts, nothing will happen. Unless you grab another different voltage. Only voltage differences make sense in physics, not the absolute values of voltages. Okay? So even a kind of voltage is unphysical. So it's fine to have unphysical values. Right, we will see some physics after all. I just wanted to annihilate, and yeah, now I can create. So it's complex conjugation. It creates a particle if there is empty space. It's only if there is empty space for it, and it again gives the same sign, which depends on all ends. Very well. Let us now do the same game we played with boson operation and annihilation operators. Let us multiply. So we look at the products. For instance, two creation operators, k and k prime. That's what we've been interested in. Let us see. We have created two particles, and we have this occupation, this vector. At the moment, this vector is still physical. It depends on ordering. Let's do it in a different order. Let's change k prime and k, and we see a different result. Because we have changed the number of particles, we have changed one of the ends which are before the last operator. And we get extra one here, minus sign. In this way, we prove that these operators anti-commute. Commutation for bosons, anti-commutation for fermions. Right? I have a special notation for anti-commutator, although it's not used that frequently as a for commutator. Fine, that's two creation operators. Well, if I would wonder about two annihilation operators, I wouldn't have to change much. Why? Because I could just conjugate these equations, right? Annihilation, conjugation of two annihilation operators would give two creation operators. Fine. What I will wonder about are products of C, dagger, C. So let's concentrate on these guys. Again, I did it rather explicitly. Two vectors I have. And I do it in a different order. So for different k and k prime, they are different. I still have anti-commutation. But if they're the same, it just gives me again occupation number. C dagger C gives me n occupation number. C dagger gives me 1 minus n. Right, sir, anti-commutation false in this particular point. So anti-commutator is 1 if k is k prime for two operators in the same level. Similar to what we have for bosons, but anti-commutation instead of commutation. Right, we can get the same, go the same way. That will be operator of total number of particles expressed in terms of creation annihilation operators, right? And again, as for bosons, we could start with this commutation relations just with operator set, which satisfies this commutation relation, and then we can make Fock space out of that. We can make Fock space out of that. Here it is. It's quite simpler than for bosons. Well, just because occupation numbers are restricted to 0 and 1. So again, any number of fermions, I could just create 1 by 1, creating them in all occupied states. Otherwise, it is cut and paste of the transparency for bosons. Okay. Structure of Fock space. Again, as for bosons, I took only two levels, 1 and 2, but it's not an infinite grid as for bosons, it's fermions. So eventually I would have only 4 points. 0, 0, 0, 1, 1, 0, 1, 1. Right. And now if I can navigate, I can move from side to side with the help of creation annihilation operators, but owing to anti-commutation, the result will depend on the way I go. If I do it like this to come to 1, 1, or like this to come to 1, 1, I will have difference inside owing to anti-commutation of creation operators. Each encodes the fact that the wave function is entirely symmetric with respect to any exchange of particles. Fine. Got a bit tired to see this again and again. Okay, it will answer. Right, so again the same program, Hamiltonian, single particle Hamiltonian. What is the difference with bosons? Well, I did precisely the same procedure. The only point now I have to care about spin, so I have extra index. When I go to coordinate representation, fermions do have spin. Well, most of single particle operators do not depend on spin, so I just put it here and here, summing up over spin. Right. Interaction. Again, I did the same procedure, express density operator in terms of creation on field operators, substituted, extracted self-interaction. That's what I convey. The only thing to care about is spin index, right? In my case, interaction doesn't change spin. It doesn't change spin, so one of the spin indices of incoming particles, here they are, created particles, has to match spin indices of outgoing particles. Conservation of spin incorporated into this Hamiltonian. Right? Last point, I hate to let you see this again, but sometimes confusion points are not that bad. You're motivated to think deeper about something. But, well, the evolution equation for field operator for fermions is identical to that for bosons, except spin index, of course, and that to Schrödinger equation. Confusingly, wave function even has a spin index, but don't get caught at this point. Fine. We almost there. Oh, am I so fast today? Good. So you have. Yes, please.
In the creation and annihilation operators, can you also include like a sigma to specify the speed that you are creating?
I did. It's just about notations. I wanted to go a little bit fast. So this small km, it includes spin. Only if we go to, so all this case do include spin. Only if we go explicitly to wave vector representation or coordinate representation, we have to recall that it's not only coordinate on momentum or momentum, the particles also have spin. More questions? Quite a big chunk of material gas. You look a little bit depressed today. Then let me sum it up and have questions if something does not fit. Right. So it's a summary of lecture 2 and lecture 3 taken all together. In principle, it's all that we want to know so far. Extraction of all material we want to know, and what we will apply in subsequent lectures. Good. So I have two columns for bosons and fermions. Right. First, wave function. Symmetric for bosons and disymmetric for fermions. Symmetric and disymmetric with respect to what?
Particle exchange operating.
Particle exchange, right? So you just exchange particles 1, 2, or 100, 101. You exchange particles, and the wave function is symmetric or disymmetric with respect to any particle exchange. There are a good set of student presentations. If you haven't chosen one, who has not chosen yet the presentation? Okay, you ought to choose anyons. That's a nice presentation about anyons, which will confuse you completely about bosons, fermions, symmetric and unsymmetric functions. So there are particles which obey any statistics, anyons. Right, then occupation numbers. Occupation number, well, it's big news, but if you derive it just from commutation relations, it's indeed the news. Occupation numbers are integer and non-negative. Fine for bosons. For fermions, Pauli principle, we have either 0 or 1. Okay, that was still lecture number, oh yeah, I've forgotten about Fock space, but it's the same. So in Fock space, remember, we applied symmetry postulate and we thrown away lots and lots of states. Remaining states are identified by a set of occupation numbers. Right, so annihilation creation operators. For bosons, they commute. Not the whole truth. They commute in this way for a dagger. So if differences are different, if indices are different, they do commute. The same index, a dagger, a gives you 1. What do we have for fermions? Anti-commutation relations. They anti-commute almost everywhere except the same level. Important concept is a field operator, creation, annihilation, not in a certain level, but in a certain point of coordinate space. Could be, by the way, a certain point in momentum space. One could introduce field operators in a different way, but well, coordinate representation, that's most convenient one. Right, so we have to invoke eigenfunctions of our levels, and here spin is incorporated in this small label K. Wave functions might be spinful. Yes?
Is the field operator like creating particle or a boson or fermion at a certain point or with a certain wave function in space?
It creates particle, it adds a particle at a certain point. Again, for bosons, for fermions, no difference. Which, I mean, you have created it at a certain point. It means that you don't know what did you do in level representation. It's a superposition state where a particle could be in many levels. Fine. Example Hamiltonian. For uniform system, I put uniform because I want to have conservation of momentum over here. Right? And here, in principle, I should have kept the spin index, but just for convenience, I did not. So I would let it as an exercise. Put spin indices in the way you like. Anyway, what we have learned is that single particle operator is very simple. Quadratic increation-elation operators. Two particle integration involves 4 creation and annihilation operators. Good Heisenberg equation for field operators. Same as Schrödinger equation, believe me or not. And that's it. That's a summary which I want to give you. Right, so real life starts from this lecture. I hope I will release homework today in the evening. In principle, we are ready for the battle. There will be problem-solving session on Monday, and we will give you some examples how to work practically with creation and annihilation operators, from very simple examples to rather fancy ones. Good. Thank you for your attention. So thank you, Zoom participants.